All right, so if you remember, a geometric sequence was a sequence that you basically multiply the previous term by some ratio to get the next term, and then you keep repeating that, right? Okay. So every geometric sequence was of this format right here that says a sub n is equal to a sub 1 times r to the n minus 1. Okay. Every geometric sequence is developed that way. Okay. So we saw things like, 2, 4, 8, 16, 32. Okay. So r in this case would be 2, right? So take this one multiplied by 2 to get that one. Take that one multiplied by 2 to get that one, right? Okay. Take that one multiplied by 2 to get that one. So then this sequence would be found by taking a1, which is 2, times r, which is 2 as well, raised to n minus 1. That's the formula for finding that geometric sequence. We did that probably 2-3 days ago. Okay. Now we can add these things again, much like we did with arithmetic sequences. Okay, we can add arithmetic sequences, and they turn into series. Okay, I can take a geometric sequence, put plus signs in it, or minus signs, and it turns into a geometric series. Okay, and if it turns into a geometric series, then because of these plus signs and minus signs, we can add them together. Okay, as much as of the series that we want to together. Okay. And the formula that is going to allow us to add these together, okay, it says the sum S sub n again of a finite geometric series, finite meaning that it ends, right? Okay, is of the series A1 plus A2 plus A3 ... A1 times R to n minus 1. R cannot be 1. If R is 1, it's not a geometric series. Can be found, that sum can be found using this formula, where we take a sub 1 times 1 minus r to the n all over 1 minus r. So you find your r, you find out how many terms are in your series, and you know the first term of your series, you have enough to add that geometric series together. Okay? Is that something we can do? Pluck out those 3 values out of a geometric series, run through that formula, and you should get your sum. Okay? So if I look at this one, I want to find the sum of this finite geometric series. So what we're going to do is say sum sub n is equal to a sub 1. So a sub 1 is what in this case? 3. I'll go 1 minus r. What's r? What am I taking and multiplying each previous term to get the next one? 2. Okay, now n. Think about what n is. N is the number of terms that we're adding together. Because of these ellipses, we don't really know how many that is, right? So I'm just going to put n in here for now as just n. And we'll have to do some scratch work on the side to see if we can figure out what that is. And then 1 minus r would be 1 minus 2. Is that okay? Now let's go find n. Okay? In order to find n, we need to know it's a geometric sequence. So this thing here is developed by a sub n is equal to a1 times r to the n minus 1. Would you guys agree that that is your nth term? So that's what this says here. That a sub n is 3072. 3 is your first term. R, we said, was 2. Raise that to the n minus 1. Now we have a equation we can solve for n. What do I do first? Well, it can't. Can I do that? Because remember, this is an exponent. Okay, I want to divide by 3 for both sides first. Okay, and I know I can't multiply those together because of the argument. Let's say that like if I had 3 times 2 to the third. If I type that into my calculator is going to give me 24. If I thought it was 6 to the third, type that in my calculator is going to give me 216. So those two values are different, right? Okay. So in this case, I want to divide both sides by 3. Okay, what's 30 divided by 3? 10. What's 72 divided by 3? 24. Equals 2 to the n minus 1. A couple different ways we can do this. Anybody remember how to solve an exponential equation? Do we remember how to solve this exponential equation? No, I can't do that. There's actually 2 things you could do here. I could take 1024. So let's think about this. If I take 2 and raise it to the n, let's let n equal 1. That gives me 2. If n is 2, it gives me 4. 3 gives me 8. 4, 16. 5, 32. 6, 64. 7, 128. 8 is that. 9 is that. 10 is 1024. Maybe if you knew that 1024 could be rewritten as 2 to the 10th, and the right-hand side was 2 to the n minus 1, because those bases of 2 are the same, what can I now say about the exponents? If the bases are the same, don't the exponents have to be the same? So then that would give me n to be 11, right? Okay. I think that is a technique that probably escapes a lot of people, mainly because common knowledge doesn't say that I know that 2 to the 10th is 1024. Most people don't know that. Okay. So what I would do here is with that 1024, when we had 1024 equals 2 to the n minus 1, do you guys remember taking the logarithm? Take the log of 1024 and take the log of 2 to the n minus 1. Do anybody remember what happens when we take the logarithm over here with this exponent? Where's that exponent go? In front. So we get n minus 1 times log of 2 equals log of 1024. Let's get that n minus 1 by itself. So we divide both sides by log 2. Divide by log 2. So we get log of 1024 divided by log 2 equals n minus 1. How do I solve for n then? How would I solve this for n? Well, it says n minus 1. How would I, if this was 10 equals n minus 1, how would you solve for n there? I'd add 1, right? So I'm still going to just add 1 here and add 1 over here. So then I'm going to grab my calculator and I'm going to ask it to go log 1024 divided by log 2 plus my 1. Does it give me the 11 that we used or found this way? Okay. Could I do this? Could I take, because I know some of that, it was a while ago, might escape us. Okay. Can we take, once we write the equation of 3072, can I say y equals 3072, and then take the equation, or sorry, the expression y equals 3 times 2 to the n minus 1, but because I want to graph it here, I'm going to use x instead of n. And when in Desmos, to get all of my exponent, I got to have that set of parentheses around it. If I do that, okay, and let's set this thing back up to have the grid shown. I want the axes there. So I got to find 3072, which is a y value that is way up here. There it is. So I'm looking at where the blue graph intersects the green graph, and when I select that point, does the x value give me 11? Does that kind of make sense? So I think that'd probably be the most efficient, maybe most successful way of finding how many terms are in our list. Okay, because if they give you a problem like this, okay, you're always going to have to go through this red stuff or this black stuff to find in. But now we know it's 11. So I can put 11 there. And now when we take our calculator and type that in, we get 3 times 1 minus 2 to the 11th. We'll divide all that by 1 minus 2. And 6141 would be that sum, 6141. Okay. And what this formula allows us to do, think about this, and it's only 11 terms. It's not a huge deal. Well, I can use maybe Excel to show you that, 3, and then what we had 6, and then we had 12, and then 24. I think if I do that, it'll give me, nope, it won't. So for whatever, I don't know what the pattern that Excel is trying to create there. Let's go ahead and say, let's do it this way. So we know, just to get Excel to use this, we know A sub n is equal to A1 times R raised to the n minus 1. We know that. So what I'm going to do, let's cut that, put that rule here. I'm going to let this column be my n value. So n is 1, 2, 3. Then I'm just going to write the rule. Okay, so if this is, so we said our first term in that sequence was 3. So 3 times then R, we said R was 2. And then we'll raise that to the n minus 1. Well, n minus 1, that's n, and we'll subtract 1 from it. So this rule I just typed in, this formula I just typed in, I just want to demonstrate to you, I'm not asking you guys to use Excel, I just want to demonstrate to you that this 6141 can be found by maybe just some brute force algebra. Okay, so you find the first term, the second term, this should be 12, the next one should be 24, 48, 96, okay, and those are exactly what we had, 3, 6, 12, 24. Now I should see that we get to 3072 at some point. There's the 3072. So what we're trying to do is add those up. Does that make sense? So you could find those 11 and then just take your calculator and say, okay, once I write those 11 down, add them together. Okay? But now here's my question. What if they ask you to add the first 111? Do you want to do that? No. Okay? It's not bad if I've got Excel and I create that formula, but maybe creating that formula, I mean, there's some learning with Excel to be able to do that. But if we go equal sum of those, it does give me that 6141 that we found using these formulas. Does that make sense? Okay. Let's do one more. All right, so what is, when I look at this, what is the ratio? What am I doing to each one of these numbers to get the next one? You're dividing by 2. So R though is always, we're always viewing it as a number that we're multiplying by. Okay? So if I'm dividing by 2, what's the same thing as dividing by 2 but using multiplication? Multiplying by 1/2. Okay? And the way that if you don't want to view it that way, you always go to the second term and compare it through division to the first one. What's 2 divided by 4? 1/2. What's 1 divided by 2? 1/2. Okay? So, but that's R has to be 1/2 here. If I let R be 2, if I thought divided by 2, then when I multiply in my formula, these would be increasing from 4 to 8 to 16 instead of going the other direction. Okay? So, if I want to find the sum of the nth terms, that's going to be a sub 1 times 1 minus r to the n all over 1 minus r. Do I know the first term? A sub 1 is 4. 1 minus, do I know r? 1/2. Do we know what term that is right there? No, that's the nth position, right? And the nth position tells me what n is in this formula. So I don't know that n yet. But I know 1 minus r on the bottom be 1 minus 1/2. So I know all that stuff. Okay? Just like the last problem. Now, we need to go to the side, and however you want to do it, we'll do it all ways. Okay? You need to be able to find out what is n. So, if I say a to the nth is equal to a sub 1 r to the n minus 1, every geometric sequence abides by that. We have 1 over 128 as our nth term over here. Okay? A sub 1 we have as 4. R we have as 1/2. But this n minus 1 we're uncertain of. Okay? How do I get this 4 to the other side? Divide by 4. So then I'll divide here by 4. So 1 over 128 divided by 4 is 120. It'd be 1 over 128 times 4. So 128 times 4 is 512. So 1 over 512 is equal to 1/2 to the n minus 1. Just like the last question, how do I get that n minus 1 out front? How do I get that out of the exponent? Can I use logarithm? I go log of the left side, so log over, or of 1 over 512, and then take the log of the right side, so it'd be log of 1/2 to the n minus 1. But then we know that that n minus 1 can come out front. And now we have this. And now, like the last example, we then divide by the log of 1/2. We get log of 1 over 512 divided by log of 1/2. And that equals n minus 1. How do I solve for n? Add 1 to both sides. So I would get, we're going to have to use our calculator to get this. If I go log of 1 over 512 divided by log of 1/2 gives me 9. Add 1 to that, you get 10. So n would be 10 in this problem. So 9 would equal n minus 1, so 10 equals n. Okay. Another way of doing it is to say, okay, well, what if I take up here where we had 1 over 512 is equal to 1/2 raised to n minus 1. How can I rewrite this side here this way? What happens is I can rewrite 1 over 512 as 1 over 2 raised to the 9th. And now because the 1/2 are the same, these exponents have to be the same. I think that's hard because not a lot of people know that 2 to the 9th is 512. Now we did know that 2 to the 10th was 1024, so maybe 2 to the 9th is easier to find because we knew that. But graphing, could we do it this? So I've already got this. So let's just say 1 over 512, and then this would have been 4. This would have been 1/2. Okay. Now I've got to go find that 1 over 512, so it's going to be down here. And we've got to find that intersection point, which here, it might not be as easy. Make sure I got this typed in right. Oh, I'm sorry. Get rid of that 4, because it's 1 over 512 and 1/2 to the n minus 1. So get rid of that 4. Sorry. Does that make it any easier? I mean, so what kind of stinks about this is this one, because that number is so small, for whatever reason, Desmos wasn't showing me that gray point until I clicked on it. So I don't know if using the graph there is the best tool. So that's why those are the types of things. We always say, hey, use the graph if we get stuck. But there's going to be times where the graph, because it gets stuck too. Yeah, like understanding the way it's programmed, and certain numbers and values might not represent or be presented the same way we would expect it to on all problems. So what is our safety net when the graph doesn't work? Our safety net is the algebra, okay? Which some of us might think it's not really a safety net because the algebra is harder, but the algebra always works and will never let us down. Sometimes programs do let us down. But then, so now we know that n, like we said, n was 10, right? So now I'm just going to plug this number right there to be 10. So going to this, we would have 4 times 1 minus 1/2 raised to the 10th. Then divided by 1 minus 1/2. And all that's going to add to that number right there. Okay? Which if you see on Desmos, it gives me this button here. So it'll convert it to a fraction. So if I were to add all those numbers up, starting at 4, going to 2, going to 1, going to 1/2, going to a 4th, going to an 8th. If I add all those up, the first 10 of them, they're going to add to that fraction right there. Okay. Tomorrow, what I want to talk about is the idea, what if I gave you What if what if we had like a rectangular pizza? Okay. And we cut it in half and I eat a half. I eat half. Okay, hold on. Then the remaining half that is left over, we cut in half again. And then I eat that half. Oh, just hold on. Just think about this. And I do that. Hold on. And then I cut it in half and I eat it again. And I cut it in half and I eat it half again. And I cut it in half and I eat it half again. I can infinitely do that, right? Does that make sense? I can always cut it in half and eat something. I can still cut it in half. No, so it's going to be very small, but I can always cut something in half. Okay? Tomorrow we'll talk about how many pizzas I ate then when I did that. Yeah. We'll talk about it tomorrow.